So okay, the big question is then, how do we actually go ahead and calculate what M is? How do we go ahead and calculate what M is? Well, it kind of comes down to this idea of how we know how the distribution is going to be spread. Okay, so if I just draw out a normal curve for you, so if I just draw out a normal curve just like this, and you've seen this drawn a million times, okay, if I draw out a normal curve like this, okay, I know that the true population mean should lie in the center. Okay, in fact, let me make this a standard normal distribution. So let me just say that that's 0. Let's just assume that the true population mean is 0. Then I know that I've got sort of 3 standard deviations each side. So this is just sort of using our knowledge of the normal distribution. And it should be the case that I should be able to work out roughly the percentage of data that should lie in this particular region here. Okay, so let's have a think about this, right? Let's suppose that I want my confidence level to be, what shall I do? Let's do a 95% confidence level, okay? Oops, level. Okay, so I'm going to do a 95% confidence level. Now I'll talk a little bit about what that means in just a second, but effectively, what I want you to take away from a 95% confidence interval is I want 95% of my data to be included. Okay, so if it's a 95% confidence interval, I want 95% of my data to be included. Now, if you think about it, I need to choose some value on this curve, because of course it's going to be centered around sort of some central value, and the central value is of course going to be the sample mean. Okay, I want it to be that 95% of data is going to be included. Now I happen to know, and I'll talk to you a little bit about how I can find that if I use 1.96 standard deviations above and below the mean, and look at that interval in there, that is going to correspond to 95% of my data. So 95% of my data is going to lie between 1.96 standard deviations above and below the mean. Okay? So obviously, you need to think about how you can find this 1.96, because this is going to be crucial. How do I find that 1.96? Well, think about it. I wanted to find 95% of my data. Now I know that 100% of my data should be lying underneath this curve. And you can see that it's obviously symmetric. Okay, so I've got equal tails, equal sort of intervals each side. So the amount on this side has got to be exactly the same as the amount of data shaded on this side. Which means that if I look at the tails, so if I look at the kind of extreme values, the data down here and the data down here should just be evenly split amongst whatever's left over. So if there's 95% of data in between these two values, then that means that 5% has got to be split on each side, because it's got to be symmetric. Which means that on the left hand side I'm going to have 2.5%, and the right hand side I'm going to have 2.5%. Okay, so just remember, all a confidence interval means is it's simply asking the question, well, I want 95% of my data. What values, how many standard deviations above and below the mean will give me 95% of my data? Okay, so really, if I just bring up my tables over here, okay, if I want to find 95% confidence interval, remember my tables are cumulative, I just need to find what this value is here. So this value is here going to be corresponding to 2.5%. So I'm going to look in the tables at 0.025, okay, in fact 0.0250, because it's given to 4 decimal places in the tables. So I'll have a look, okay, and I'll look in the tables and I go, okay, I'm just looking, and you can see here that 2.5%, so 0.0250, is going to be negative 1.96, so bang on. You can see that 0.250, negative 1.96. And obviously, because it's symmetric, if I want 2.5% up here, I'm going to look at 1.96 values, 1.96 standard deviations above and below the mean. So just remember, the reason why I'm looking at this particular curve here is because I want to do this in terms of standard deviations. I know that for a particular data set, which is normally distributed, if I want, in this case, 95% of my data above and below the mean, so 95% of my data included, I'm going to be looking at 1.96 standard deviations above and below the mean. In which case I need to look at the extremes. They're going to be split on the remaining 5%, so 2.5% and 2.5%, and then from there I should be able to find how many standard deviations I need to look at above and below the mean. Now, here's the thing, Okay, just remember up here that what I was doing was taking lots and lots of samples. Okay, so in this case I took 3 samples. Now we know, using the central limit theorem, that if I take lots of individual random variables, so let's assume that x is going to be normally distributed with some mean and some variance. Okay, if I take sort of several samples, each from this distribution, so all of the random variables will be from this distribution, I know that when I put them together and take the mean, that they are going to still be normally distributed, they're still going to have the same mean, however, the variance is going to change, the variance is going to decrease, and you saw this from this curve here, right? The variance is going to decrease, and it's going to decrease by a factor of n, so in other words, in relation to our sample size. So it's going to be sigma squared over n, which goes here. So this is just the central limit theorem, okay? So if I take n samples, so in this case, instead of just taking a selection of 5 words, if I now do it again, and then I keep doing it over and over and over again and taking the mean of each of those samples, then I know that my normal distribution is going to change like this, okay? So, just remember that I said down here, if I want to be 95% confident that my mean, my true population mean, lies in this region, I need to include 95% of my data. Okay, in which case I know that I need to be looking at 1.96 standard deviations above and below the mean. So if you think about it, looking at this is now my variance, okay? My standard deviation, so my variance of x bar, is sigma squared over n. That means that my standard deviation of x bar is going to be equal to the square root of this. So if I take the square root of it, I take the square root of the top, square root of the bottom, I get sigma over root n. Okay, so that is now my standard deviation. Now, because this is kind of my standard deviation, and I know that I need to be looking at 1.96 standard deviations above and below the mean in order to include 95% of my data, so I need to be 95% confident that my true population mean lies in that interval, then I just simply need to construct m in relation to this. So I know that m is just going to be 1.96, that is the number of standard deviations which I need above and below the mean for 95% of my data to lie in that interval, okay? And I just need to times 1.96 by whatever my standard deviation is. Because remember, this is units of standard deviation, so 1.96 units of standard deviation, okay? And my standard deviation is going to be this, so sigma over root n. Okay, so in other words, this is how you calculate n, right? So really, all that's going to change is this 1.96. If I change it to look at, say, like a 99% confidence interval, then this is what's going to change. If I look at a 90% confidence interval, then this is going to change. If I look at a 50% confidence interval, this is what's going to change. So this is always the units of standard deviation, and this is how many. This is what each standard deviation is worth. This is the value of the standard deviation. So, okay, we'll look at a few examples in just a second. So essentially, what I'm saying is that my true population mean should lie between some interval above and below the mean. And the interval is x bar minus m and x bar plus m. This is literally what this was saying down here, right? So I took x bar, then it's going to be x bar minus m and x bar plus m, and the m is decided according to how confident you want it to be. Okay, so if you want 95% confidence interval, you need to include 95% of your data. And you know, on average, 95% of your data will be included by looking at 1.96 standard deviations above and below the mean, where the standard deviation is given in terms of this. Okay, so sigma over root n. Okay, so in other words, I could write this as x bar minus m is just equal to 1.96 times by sigma over root n less than or equal to mu less than or equal to x bar plus sigma over 1.96 times by sigma over root n. That's just simply replacing m with this thing here. Okay, it's just simply replacing m with this thing here. So this here would be my confidence interval. This is my lower level and this is my upper level. Okay, so this is how I define my confidence interval.